Hi everyone, I'm Giovanni Pittillo, Research Fellow at Boston Children's Hospital, Harvard Medical School. Today I'll talk about work in the University of Leeds, where I was doing my PhD with Pietro Valdastri, working on collaborative magnetic manipulation, where we wanted to add magnetic degrees of freedom when we were controlling catheters inside the human body using magnetization. So in this case, we've been looking at different alternatives. So we've been looking at permanent magnets at the tip and distributed magnetization on the structure of a catheter, as well as recently I've been looking at how we can do magnetic catheters using magnetic spheres which bond to each other and form spherical-like joints, and we can add magnetization to them. Today I want to talk about how we could actuate these systems, and we don't think there is a straightforward answer, but we think that when we can use permanent magnets, we have a higher density of magnetic field, and so a higher force and torque that we can apply on these systems. So when we can move and rotate them freely around the body of the patient, we have a good level of controllability as well, as we've shown in our previous works, where we could see we can even levitate the tip of an endoscope using an external permanent magnet in real-time localization. And what we can see here is that even if we apply external inputs that we cannot predict, we can still have a stable control. And in this case, we use one permanent magnet outside, which being robotically actuated. As you can see here, it moves as the endoscope moves, sorry. And in this case, we have up to 5 degrees of freedom control, because as we rotate the magnet around its main axis, we don't change the field we've been applying. And so we took inspiration from work from Sajal Salmanipur and Eric Tiller from ICRA 2018, where they looked at controlling multiple degrees of freedom, up to 8 degrees of freedom using 8 coils. And what that means is that if we have a magnetic element in an environment where we are applying magnetic field and consequently gradients, we have that the force applied to this magnetic element relates to the gradients, and the torque relates to the magnetic field. Now, given Maxwell laws, we know that the divergence and the curl of the magnetic field has to be 0, and so just 5 of the gradients or the elements that relate to the gradients can be controlled independently if we have an appropriate system to control them, and plus the 3 degrees of freedom of the magnetic field, we have 8 degrees of freedom that they can control with a system of 8 coils. And so we asked the question, can we do that using permanent magnets? And we ended up with the answer of using 2 permanent magnets to do the same task. And so in this case, the system becomes much more nonlinear, and the target is how we can control the field and the gradient at a point we select by moving these magnets around. So you can think of it as a problem of inverting the kinematics, where we don't just want to position these end effectors or magnets outside the body of the patient, but we're looking at what kind of magnetic field and gradient they produce. And so I skipped the maths because it would be too long here, but we can use these as an inverse kinematics problem, pretty much. And so here I show what we did using simulation. So here are some results using simulations of this inverse kinematics problem, where we looked at multiple combinations of fields and gradients that we can control, and then we feed that to our inverse kinematics, and the green points you can see here are the points where the end effectors or external magnets were practically positioned to generate these fields. And you can see it's like a shell-like structure, and it's hollow in the middle because we are using polar constraints so that we avoid the magnets to invade the patient that we reserve to the patient. And we also looked at 2 alternatives. One is like kind of ideal, where we can position external permanent magnets freely and rotate them freely around the body of the patient, and these are the polar constraints. The polar constraints you see here. And if we add kinematic constraints that relate to the robots, we have an increase in error, but still 76.6% of the samples we looked at have an error related to them of less than 1%. And so we've done many experiments to validate that, and I can show one of them as a matter of time. And here what we looked at is how we could manipulate the force and torque on 2 internal permanent magnets, which are held by 2 load cells. In this case, the load cells can measure 6 degrees of freedom. The permanent magnets are orthogonally magnetized, because if they were parallelly magnetized, they kind of behave as one magnet when they're too close to each other. And we are moving the external magnets so that we can manipulate these 8 degrees of freedom. and we can track where the internal magnets are with respect to external magnets using an optical tracker. And so we can use this information to infer what is the field that we expect and what is the field that we would use to invert the kinematics, which is predicted from the dipole model, and is the dashed line you see here, whereas the solid line is what we measure from the load cells. And these are 8 of the degrees of freedom that the load cells can measure and the ones that we can actuate. So the error is the discrepancy between the dashed line and the solid line when we are at the steady state. Crosstalk means a degree of freedom that is activating when it's not supposed to activate, and we can measure max as a 6.1% error crosstalk and 11.1% mean error. And we can see that we have transitions between these set points that we cannot predict, and we can see spikes. And this is the disadvantage of using permanent magnets, because as compared to coils, we cannot switch them on and off. And so we have to move the magnets, and as they move more point to point, in this case, we see these spikes that are undesirable for clinical application. So what we're looking at is how we can move them to have a smooth application of magnetic field and gradients. So to conclude here, we looked at how we can control 8 degrees of freedom magnetically using 2 external permanent magnets. And we have already applied this technique to autonomous navigation and closed-loop control using fiber Bragg grating running through a magnetic catheter. And in the future, we want to combine these together with a planner that can smoothen the navigation and altogether improve safety and overall outcome of the autonomous navigation. Thank you. I'll happily take your questions.